This short video just discusses the substitution and elimination chemistry of amines. Below here is a structure sec-butylamine. We have a butyl group through a secondary carbon connected in a single bond to a nitrogen. If we would have had two of them, it would have been N disec-butylamine, just like we can have N trimethylamine, or we can have just a methylamine. We can have an indication of how many alkyl groups are on this by hearing the word or letter N. So we can say this would be sec-butyl amine. But again, if you hear the letter N, it means it's off the nitrogen. So we might have N-methyl sec-butylamine, where we know there's another alkyl group off the nitrogen. All that said, I want to talk about two substitution reactions and one elimination reaction involving amines. So we'll go to the north when we are looking at substitution reactions, and we'll look at one elimination reaction. So the first reaction is sort of a runaway reaction. We can take the nitrogen, sp3, partially negative, as a good nucleophile, and we can react it with just something as simple as methyl iodide and have an excess of this. And using a scavenger, maybe potassium carbonate, something that can keep the acid concentrations down if generated, to scavenge those protons off, will help drive this reaction. So let's look at the first step of the reaction. We know this is a fairly good nucleophile. It's a fairly basic site. So we could propose with a methyl iodide an Rx that has no beta protons. We could propose a substitution reaction wherein we start to connect the carbon here to the nitrogen here at the same time that we're kicking off iodide. So an SN2 reaction. We could propose an SN2 reaction for methyl iodide and our sec-butylamine. We would immediately get a alkylation of the amine, where the nitrogen using its lone pair would have a full positive. We'd have kicked off iodide, and we'd have our first substitution reaction. But the problem is, this reaction doesn't stop. Given our scavenger will take the proton away, we would put a lone pair right back on the nitrogen. It would have another partial negative charge, and it would be just as reactive for the most part, maybe a little bit different. It would be just as reactive as the starting sec-butylamine we would have made if we tear the proton off with our acid scavenger. We would have a nitrogen that's very, very similar to this one. So it'll continue to be alkylated, to be methylated. So this would be methyl, N-methyl sec-butylamine, but it could continue to go two more times until we take off all protons and even add a third methyl group, because we have the ability for even a N trimethyl sec-butylamine to go all the way to N trimethyl sec-butyl ammonium iodide. We can call this, just in general though, an ammonium ion. This nitrogen now has a positive charge. We can no longer alkylate this. I mean, there is no lone pair. After you put the third methyl group on, you've exhausted your capabilities here. It's a full positive on the nitrogen. This can serve as a very good phase transfer catalyst, having a lot of organic groups around it for organic phases, but having a positive and a negative charge associated with it that can give it some solubility in water. So this is just an alkylation reaction. We've used methyl groups for this alkylation reaction. We could have used an ethyl group to alkylate this nitrogen. You can make in this way tetrabutyl ammonium bromide, a very common phase transfer catalyst. But what if we didn't want to go all the way to full alkylation of this nitrogen? What if we just wanted to have a synthesis of a primary amine, not a quaternary amine having 4 alkyl groups off a quaternary ammonium ion? What if we didn't want to go all the way to having 4 alkyl groups off of this? What if we just wanted to have just 1 group off of this nitrogen? Well, we can do that through a way called Gabriel synthesis. We can take, and we're going to propose the reagent used in the Gabriel synthesis, phthalimide. We're going to take and use a reagent that will allow this nitrogen here, that will really be in the end, this nitrogen here, to be alkylated just once. So we can make primary amines, meaning having just 1 carbon off of them. So the way we can do this is we can take a base, and it doesn't have to be really strong. We can drive the reaction with KOH here. And if we had trouble with the attack of this carbon here, we could use a bulky base. But we can make the anion from this imide. It's called the imide. This is an imide. So we can take the anion from this imide that we make using a base, and we can add our sec-butyl chloride. We can add that sec-butyl chloride at that point. Then we would have our SN2 reaction, because this is just going to act as a weak base towards a secondary alkyl halide. This is a weak base because the nitrogen gives us some delocalization into the oxygens of its negative charge. This alkyl halide, secondary RX, weak base, we can propose a SN2 product here, the alkylated imide. Once we're at this point, we can make this primary amine. Again, Gabriel synthesis is used often to make the primary amine. We can finish the reaction by just removing this part of the structure, cutting these carbon and nitrogen bonds by an acid with water workup or a base with water workup. With a lot of water and base, we can start to make the carboxylates from this, or we can make carboxylic acids and drive this nitrogen off through protonation. So we can break the imide structure in this alkylated imide to give us and release free this nitrogen with protons and the sec-butyl group. So that's a complement to the runaway reaction here, where we cannot stop alkylation. Here we stop alkylation of the nitrogen to just 1 alkylation, because we've tethered it to these carbonyls, and we can break those carbonyls off when we want to do our workup in water. Okay, our last reaction I want to talk about is a Hofmann elimination. Hofmann elimination. Really, we see these when we have very bulky nucleophiles attacking alkyl halides. We tend to make what we call Hofmann elimination products, where the double bond that's formed in the elimination is between the carbons that are least substituted. So to start this Hofmann elimination off, we have to make a very bulky leaving group. We're going to make a bulky leaving group. This nitrogen is not going to be a great leaving group, but what we're going to do is have the excess, just using methyl iodide, and we'll use that acid scavenger. And if we do that, what we get, if we use an excess of this, again, we get the runaway reaction to this N trimethyl sec-butyl ammonium cation, wherein we now have a very bulky, not great leaving group, but if this bond breaks away, this will be neutral, so it's a fairly, I don't want to say reasonable leaving group. We're going to have to drive it off though, so what we're going to do from this point is you're going to add KOH, or you can get away with silver oxide, which in the presence of water and the remaining iodide here will generate your strong base hydroxide that we need. And what will happen here is we can have now a elimination reaction wherein we don't go to the carbon that has the least hydrogens and put the double bond such that it has the most substituents. We go to the carbon that has the most, that's alpha, next to the leaving group, not to this carbon to do elimination chemistry. We always go with the leaving group 2 carbons away, so the beta carbon. We go to the beta carbon, we rip off a beta proton, but we go to that carbon that has the most hydrogens. So we want to go to the most, I guess, hydrogens as far as at the beta position. Most hydrogens at the beta position. So 1, 2 steps away from the nitrogen as far as the carbons. 1, 2, 3 protons. 1, 2, just 2 protons. So that when we kick this off, we have done it from the side, the beta side, that has the most hydrogens. So our product would just simply look like this. We'd have a 1-butene. We'd have created, of course, our leaving group, which would have as a name N-trimethylamine, or just trimethylamine. And we'd have made water using that strong base. And again, you can have silver oxide used in the presence of these ammonium iodides with water. Silver oxide in the presence of water with these can give us a little bit of hydroxide. Well, that's it. Just wanted to make a short video discussing the chemistry of amines. Not all of the chemistry. There's the use of a diazonium salt that's not covered in this video, that's very commonly seen for amine chemistry, the formation and use of diazonium salts. But just wanted to cover alkylation 2 different ways: runaway, Gabriel synthesis, makes a primary amine, and then also cover elimination chemistry that's unique to amines. Amines can be alkylated to give us a bulky leaving group, and then a Hofmann elimination where, again, remember, the hydroxide is going to the beta carbon that has the most hydrogens to give us a least substituted alkene. It's only got 1 alkyl group off of it. That's it. Bye-bye.